Hello, today we're going to be looking at lesson 5.5, which is coordinate geometry with a focus on slope. So first we're just going to describe the definition of slope. Really it's a number that describes how steep a line is. A slope can be positive or it can be negative depending on if the line is sloping upward or downward. So if a line has a positive slope, it will slope upward to the right. So always go from left to right. On the other hand, if a line has a negative slope, it will slope downward from left to right. And then the slope of a vertical line, which we'll describe a little bit later, is actually considered undefined. And the slope of a horizontal line is 0. The way that slope is calculated is essentially it's almost like a set of stairs. It's how many steps you have to go up, or the distance you have to go up, vertical change, over the distance that you have to go over, which would be horizontal change. We summarize this as rise over run. So how far up you're going divided by how far over you are going. And slope is always calculated by going left to right. So make note of that. So in this first example, you can see we have this red line from point A to point B, and the diagram actually goes over first and then up. I typically do the rise first, but either way, whenever you get from point A to point B, go left to right, you have to go up 8 units when you count, and you have to go over 6 units, which would make your rise over your run 8 over 6. Now that is equivalent to 4/3 simplified. So you would say that this slope has, or this line has a slope of 4 over 3. 4/3. So rise is 4, the run is 3. We could do the same thing over here for a negative slope. Again, because we're starting at the point on the left, to get to the point on the right, we have to go down. And that's why we end up with a -3 as the rise and a +6 as the run. So your rise over run is -3/6, which simplifies to -1/2. So essentially it just means for every one that you're going down, you're going 2 over. Down 1 over 2, down 1 over 2. That's the steepness of that line. So in the next example, we'll take a look at several different lines and practice calculating the slope of each. So we'll start with line A. So line A is that line in blue. So what we would want to do is pick a point. We want to get to another point on the line. So if I pick this point here, 0, 0, and I'm trying to find the rise over the run, I notice if I go up 1, then I would go over 2 in order to get back to the line. And again, up 1 over 2. So what that tells me is the slope of line A has a rise of 1 and a run of 2, and it is clearly positive. Now I could do the same thing for line B. So I can go on starting at the origin again, because clearly line B goes through the origin as well. We could go up 1, 2 over 1, up 2 over 1. And so that would tell me that this one has a rise of 2 and a run of 1. And then lastly, line C, if I'm going from the origin, and this one clearly has a negative slope, I see I'm going down 2 over 1, down 2 over 1. And so the slope of line C would be -2 over 1. If you pictured real quick, and this is not on there, but if you pictured really quickly a vertical line, the reason we say that that has a slope that is undefined, I'm just going to put one on here real quick. I could find from any 2 points the rise. So let's say I had 2 points on here and the rise was 1, 2, 3, 4. My rise would be 4 and my run would be 0. The problem is there is no way we can divide by 0, and so that ends up being undefined. A horizontal line, on the other hand, which we could put down here, if we have 2 points on there, we can find the run. Let's say the run is 2, but the rise is 0. So your slope would be 0 over 2. Well, that's okay. You can divide 0 by 2, you just get 0, which is why when we said earlier a vertical line has a slope that's undefined, a horizontal line has a slope of 0. Okay, next, we're going to take a look at some other lines here. Okay, you'll notice really quickly here that these lines look an awful lot alike. That's because they're parallel. They're never going to touch. They're going to go on forever like that. So let's find the slope of each line. So if we start at the y-intercept where it's crossing over the y-axis, we notice we'd have to go up 1, 2, over 1, 2, 3. And so my slope there is 2/3. So 2/3 slope for this line. Now I'll do the same thing, but this one starts down here. So we go up 1, 2, and over 1, 2, 3. So this one also has a slope of 2/3. And what I was hoping you'd see here is that if we have two parallel lines, no matter what, they're going to have the same slope. So the slopes of parallel lines are the same every single time. And it makes sense if you think about it because they look the same steepness. They, in fact, are the same steepness. Okay, let's try this next one. So we're going to find the slope of these two lines. Okay, so for the first line, I'm going to go always from left to right. So I'm going to go from this point up 2 and over 1, 2, 3, 4. And so that would give me a slope of positive 2 over 4, which is 1/2. For the other line, again, I start at the point on the left, and I'm going to go down 1, 2, 3, 4, so that's -4 and over 2. So that would be a slope of -4 over 2, which equals -2 over 1. Now, what I want you to notice about these two are they are perpendicular lines. If you look very closely, they come together and meet at a right angle. So that special characteristic also, the slopes have something in common. When you have two perpendicular lines, their slopes are opposite reciprocals. So we'll write that down. So they are opposite reciprocals. And what that means is they are opposite signs and they are flipped. So both things have to be true in order for the two lines to be proven perpendicular. So in example 4, this is just a way to look at slope. So given the slope of a line that is parallel or perpendicular, give the slope of a line that is parallel or perpendicular to the given line slope. So if we know a line has a slope of 4, a parallel line would also have a slope of 4. A perpendicular line, on the other hand, would have a slope of -1 over 4. So since any whole number could technically be written over 1, we want the sign to be opposite, which is why it becomes negative, and we want it to flip, which is why it becomes -1 over 4. For the next one, if we're given a slope of 2/5, a parallel slope would be exactly the same, and a perpendicular slope would be the opposite sign, so negative, and it would be flipped, so it would now be -5 over 2. Okay, next. It says graph the quadrilateral with the given vertices. Give all the names that apply to this quadrilateral, so that goes back to lesson 5.4. So we're going to plot them first, and then it says use the slopes of the sides to prove this. So we have -3, 2. So let's plot that one. That is point L. Point O is at +3, 2. Point V is at 5, -2, so that's right here. And point E is at -5, -2. So now I'm going to connect them to make a figure. So it looks an awful lot like a trapezoid, but we have to prove it. Remember, trapezoids have one pair of parallel sides. So what we notice is that the two parallel sides are actually horizontal. So if I calculate their slopes, which we wouldn't even have to really do for rise and run, the slope of segment LO, let's say, is 0 over 3, so it's 0. Then if I do OV, to get from O to V, I'd go down 1, 2, 3, 4 over 2. So segment OV would have a rise of -4 and a run of +2, which gives it a slope of -2. Then we have segment EV. We could pick any 2 points on that segment, and it really won't matter because we know this is a horizontal line. But based on what I did there, we'd have 0 over 4, because the rise is 0, run 4, and we would get 0. And lastly, EL, I always start at the point on the left, so I start at E, and I'd go up 1, 2, 3, 4 over 1, 2. So that's +4 over 2. So this is segment EL. My rise was 4, my run was 2, giving me a slope of 2. So now when I have to give all names that apply, I notice that segment LO and segment EV are parallel. And because of that, I know that I have just one pair of parallel lines in the figure. Now some of you might be thinking, does that make OV and the EL perpendicular? No, those are not perpendicular. Even though they have opposite slopes, they're not reciprocals, so they're not considered perpendicular. So when naming this figure, we already know it's a quadrilateral, which we then know implies it's a polygon. So the only name you would have to give it is trapezoid. Okay, last one, example 6. It says graph the two lines. Are the lines parallel, perpendicular, or neither? And explain using the slope. So we're going to start with line AB, so make sure you do these separately. So A is -3, -4, so that's going to be down here. B is 2, 2, so to the right 2, up 2. And this is a line, so we'll do our best to make a straight line. Arrows on either end. Then we have line CD, which is at -4, 4 for point C, and 1, -2 for point D. Okay, and now I have to find the slope of each line. So we'll start with AB. So for AB, I have to go up 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5. So AB has a slope of 6/5. Then for CD, from point C, I go down 1, 2, 3, 4, 5, 6. So that's down 6 over 1, 2, 3, 4. Whoops, I went 1 too far. Let's count again. 1, 2, 3, 4, 5, 6, and then over 1, 2, 3, 4, 5. There we go. So that is a slope. Okay, sorry. So now we can calculate the slope for CD. So when we went down 6 and over 5, that gave us a slope of -6/5. Now, we have to declare if these are parallel, perpendicular, or neither. At first glance, we might think they're perpendicular, and they're awfully close. But in order to be perpendicular, they have to be opposite signs and reciprocals. These are only opposite signs, which means that we would say they are neither. To be parallel, they would have to have the same slope, and to be perpendicular, they would have to have opposite and reciprocal slopes. These ones are just opposite.